Hi, it's Tom. In this video, which is the fourth in a series about data types, what we'll do is we'll write a program that helps us understand some of the technical details of the floating point family of data types in C++. The most obvious difference between a floating point and an integer is that integers hold whole numbers and floating points have the ability to hold numbers with fractions. Now, whole numbers are really easy to represent in memory. Basically, we convert the number into a binary format, and the binary digits are the ones and zeros of the number. That's really very easy to represent in bits. Floating points are a little bit more complicated, and there's more to it. So let's look at an example of a floating point number and how the bits are broken down. Found a little diagram that online here that will be, I think, helpful for examining this. So this is an example of a 32-bit floating point type. The first bit is basically dedicated to the sign. There's no such thing as an unsigned floating point number. They always have a sign. Then the next series of bits is actually going to be storing a number that's interpreted as an exponent. This number is used to push the decimal place in the number either to the left or to the right. The next part, or the next series of bits, and it's usually the largest part, this is what it's labeled here as fraction. This is basically the number without a decimal point in it. So if I were recording pi, for example, okay, this might be 3.14159 in binary, of course. And then the exponent would basically determine that the point goes after the 3. So this would be like 314159, and the exponent would explain where the decimal place goes. So that's the basic idea. Actually implementing this and doing mathematics with this can be quite complicated. One of the consequences of this style of storing the number is, unlike an integer, which is absolutely precise, this kind of format is prone to rounding off. There's only so many bits that we can use for keeping track of the fraction, which basically equates to so many significant digits that we can track. We can make the number extremely small or extremely large by multiplying it out by this exponent. But there is a lot of rounding off going on. So we're going to see that in our sample program as we're moving forward. So to start off with, what we'll do in our program is we'll actually create a float variable. I'm going to call it a single precision number. Okay, just declare it. And then what we'll do is we'll output some information about this variable. Starting with how large it is. Okay, I haven't bothered multiplying it by 8 here, so we're actually getting the number of bytes it takes up in memory. Followed by what range of numbers that it can hold. Now, in the previous programs, I actually calculated that. In this program, just to keep it simple, because it is pretty complicated actually, what I've done is I've actually included FLT min and FLT max, which are declared in a library called cfloat. So this just tells me the smallest and the largest number that can be stored in the floating point data type. These are expressed as positive numbers, but it could be negative numbers as well. I'm going to put a semicolon on the end of that, and we'll just run it as is. So it turns out that a float uses 4 bytes of memory, and it can hold positive or negative values between 1.75 blah 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 to the power of 10 to the power of negative 38. So imagine moving this decimal point to the left by 38 spots. Okay, that's a very small fraction. And then the upper limit is 3.4 etc. times 10 to the power of 38, positive 38. So that's like moving the decimal point 38 places to the right. So that's an extremely large number. In fact, with the floating point data types, the range of numbers from very small to very large are not especially consequential. Usually you're able to store very large or very, very small numbers in a range that far exceeds what you probably are worried about. The bigger issue with a floating point number is its precision. So what we're going to do is we're going to go back to our program. We're going to add a line in that shows us how many significant digits a floating point data type can deal with. Okay. Now to get that bit of information, I'm actually relying on a class that's defined in my library called limits. So this, it's actually a class template, which we'll learn about eventually. But the way that this works is basically I'm creating a class called numeric limits with a float. And in that class, it defines digits 10 is a named constant that tells me how many significant digits in decimal, in base 10, I can count on being able to store in a float before rounding occurs. So basically, beyond this number of significant digits, it starts getting wonky and inaccurate. So we'll run this and see how this goes. So with our float data type, I can store 6 significant digits. Okay, so significant digits are basically the digits from the first non-zero digit to the last non-zero digit. The decimal point can be anywhere in that, or far to the left of that, or far to the right of that. But that's the number of actual, the actual number I can actually store. So that's the limitation when we're talking about a float. Let's look at the other 2 floating point data types that we'll use in our program. The most common type that you're probably already used to using is double. Okay, so float is not doesn't have a lot of significant digits. Double will be double the size and double the significant digits approximately. So we'll do the same sort of thing, but we'll use float instead. Sorry, we did use float. We'll use double instead. All right. So this time I'm saying double uses size of a double, numeric limits based on a double to give us the significant digits, and the minimum and maximum values are double min and double max. Okay, so we'll go ahead and run this, and we'll see what things look like for a double. So we can see that a double uses 8 bytes of memory, which is 64 bits. It can hold much smaller numbers and much larger numbers. You can see the exponent here, 10 to the power of negative 308 to 10 to the power of positive 308. That's a lot of zeros, either before or after the significant digits. And the number of significant digits that we can count on is 15. All right. Next, we'll do what's known as a long double. So long double is literally the word long space double. That's all one data type. And we'll output, again, the same kinds of information. Okay, so a long double uses size of long double. It's LDBL min and LDBL max for the minimum and maximum. And numeric limits long double, digits 10, should give us the number of significant digits. So we'll try running this. So we can see that long double apparently uses 16 bytes of memory, okay, which would be 128 bits. It can hold positive and negative values from, now you can see here, much smaller and much larger numbers. Okay, that's a lot of moving the decimal places. 4,000 to the left or 4,000 to the right, nearly 5,000 actually. But not a lot more significant digits, okay, than a double. You might have expected this to be more than twice as much. In fact, we would expect with 16 bytes of memory, if you look at some of the standards, that's a quadruple precision number, which should give you about 70 or 71 significant digits. However, this is a little bit misleading. It's not actually utilizing all 16 bytes of memory or 128 bits of memory. The long double is kind of a hybrid type in C++. It depends on how it's implemented, by the way. It might be different on one compiler than another. But on this compiler, certainly, It's implemented as a 80-bit data type. Okay, so it's kind of extended double, but not quite a quadruple, if you will. So bottom line, we're getting more significant digits and a much larger range of numbers. That part of it typically doesn't matter. What I'm going to do next is we'll add some stuff into the code where we're actually going to test out these significant digits and see if we can prove that we're getting at least these amount of significant digits for each of these three data types. So to begin this experiment, I'm going to create a constant. I'm going to make it a long double constant, and it's just going to be this number with lots of significant digits. So it's a const. The data type is long double. I've called it significant digits, and 0 point, and then basically I do 25 digits here. Okay, so I'm saying, oh, this should be 25 significant digits, which is obviously more than what any of the data types will hold. Now I've intentionally caused a little bit of a logic error here. We'll go back, once we see the consequence of this, we'll go back and see if we can fix it. But the next stage, I'll leave it the way it is for now. The next stage is just basically to make each of these variables initialize it to this significant digits constant. So the idea being we'll get as many significant digits as we can in each of these data types. So for my float, I'm typecasting significant digits as a float. So I should be able to get at least 6 of them. For my double, I'm typecasting significant digits as a double, so I should get at least 15 of them. About to there, I would say. And then extended precision number, I should get, at least 21 of them, and there's no typecasting involved. So we'll output these numbers to actually see what we get. So I'm just going to set my output so that it's in fixed notation. So I see all the numbers, and I'm going to set the precision to 25 decimal places, which is more than I need, right? So I think I only need, well, actually I might need 25. So we can do interactive stuff. We'll play around with that number maybe a couple of times, but that's for formatting. Comparing values stored, I'm outputting the string, the same string. I just copied and pasted what the original number was, and then directly underneath it I've said float, and I've output the significant precision, a single precision number, and so we'll be able to compare them digit by digit. So let's try running that. So we can see here that the numbers are not the same. They start out the same. Okay, so it looks like about up to the 7th significant digit is the same, and then we can see it starts going wonky. Okay, so that's an example of how a float, it's actually getting to the 7th significant digit instead of the 6th before it's starting to mess it up. Okay, so so I guess we've proved that we do have at least 6. Let's try the other types. Actually, before I try the other types, I'm just going to mark off where this was to make it a little bit more obvious in the output. Okay, so I had typed this before. You don't want to necessarily watch me type. But basically, we got to the 7, which gave us 7 significant digits. So we'll just run this really quick to make sure that lines up properly. So we can see pretty clearly where the numbers are the same and where they started being different. All right, so what I'm going to do is I'm going to do the same cout statement for the other two types. Forgot the C and cout there. Okay, so we'll go ahead and run this. Okay, so string and float was fine, string and double. So where is it starting to mess up? So we get to the second 7, which is about the 17th significant digit before it starts being different. And then for the long double, let's see, it actually doesn't get very much beyond that, interestingly enough. In fact, the long double and the double are the same. That's kind of weird. So I'll add in my placeholder to make it easier to see that it's getting to 17 significant digits. Okay, I'm just going to run that again to make sure it works. Okay, so yep, they're the same up to that number and different after that dash. And it's the same in both of them. So this is curious. Why is long double the same as double? And the answer has to do with that problem that I mentioned at the very beginning, so you know I'm not crazy. It's how I actually initialize this. So the little trick to knowing what's going on is understanding that when you use a numeric literal with a decimal point in it, in C++, it's interpreting this number as a double. So that's why it doesn't matter that I set extended precision to, I set this constant, which is a long double, to this value. This value is a double, so it's automatically messing up the significant digits. To treat it as a long double, what I have to do is I have to add on to the end of it either an uppercase or lowercase l. I don't use lowercase l because it looks too much like a 1. So by adding that suffix, the compiler knows to treat this as a long double. So just by making that one change, I added the L in there. We'll go ahead and run it again. And we should notice very clearly that the long double, there's my dash, that's where we got to before. But you can see it actually does go beyond that. So 8, 9, 0, 1, and then it starts messing up again. So that's about 21 significant digits. So you may recall it was minimum of 18. So we've managed to prove, at least with this example, we've exceeded the minimum requirements there. All right. So I'll just make that adjustment in the output, and I'll run it one last time to make sure that it does in fact work. And it doesn't. Hang on. Oh, I don't know what happened there, but it's working. All right. So we can see that we got quite a good amount of significant digits out of that last example. All right, so this concludes this video. In the next video, we'll play around a little bit with floating points some more, and we'll look at some of the consequences of this whole precision and rounding off and the issues that come up from it. Thank you very much.